Imagine you're sitting in the fastest vehicle humanity has ever created. You're traveling at 163 kilometers per second. That's fast enough to circle the entire Earth in about 4 minutes. You feel invincible. You feel like you've conquered the cosmos. But here's what will absolutely shatter your perception of speed. At that velocity, it would still take you 19,000 years to reach the nearest star beyond our sun. Let me put this another way. Right now, at this very moment, there is a spacecraft called Parker Solar Probe that has achieved speeds of 163 kilometers per second relative to the sun. That's 364,621 miles per hour. It's the fastest human-made object in history. And yet, on the cosmic scale, it's barely crawling. It's moving at 0.054% of the speed of light. This is the uncomfortable truth we're going to explore today. We are simultaneously incredibly fast and embarrassingly slow. And understanding why will completely change how you think about space travel, human ambition, and our place in the universe. But before we dive into this mind-bending journey, do me a favor. If you're ready to have your understanding of space travel completely reconstructed, hit that like button right now. And subscribe, because this is going to be a 3-hour expedition into one of humanity's most pressing questions. Also, drop a comment telling me where in the world you're watching from and what time it is for you right now. I'm genuinely curious to know who's joining me on this journey across the globe. Are you watching this at 2 a.m. in Tokyo? During lunch break in New York? Let me know. Let's start with something that seems simple. What does it mean to travel fast in space? Because here's the first twist that most people never consider. There is no such thing as absolute speed in space. Every speed measurement is relative to something else. When we say the Parker Solar Probe is traveling at 163 kilometers per second, we're measuring it relative to the sun. But relative to Earth, it's traveling at a different speed. Relative to the center of our galaxy, it's traveling at yet another speed. This isn't just semantic gymnastics. This is fundamental to understanding space travel. Think of it like this. You're sitting in your chair right now, and you feel stationary. But Earth is rotating at roughly 1,670 kilometers per hour at the equator. Earth is also orbiting the sun at about 107,000 kilometers per hour. Our entire solar system is orbiting the center of the Milky Way galaxy at roughly 828,000 kilometers per hour. And the Milky Way itself is moving through space at about 2.1 million kilometers per hour relative to the cosmic microwave background radiation. So are you moving fast or slow right now? The answer is both, and neither. It depends entirely on your reference frame. This concept, deeply embedded in Einstein's theories of relativity, is the first layer we need to understand before we can grasp how fast we can really travel in space. Because when we talk about traveling to other stars, other galaxies, we're not just fighting against distance. We're fighting against the fundamental structure of space-time itself. Now, let's establish our baseline. What are the fastest speeds humans have actually achieved in space? The current record holder, as I mentioned, is the Parker Solar Probe, launched in 2018. In 2021, during one of its close approaches to the sun, it reached 163 kilometers per second. That's 586,800 kilometers per hour. To put that in perspective, if you could drive a car at that speed, you could travel from Los Angeles to New York in about 7 seconds. But Parker Solar Probe achieved this speed through a clever trick called a gravity assist. It used Venus's gravity like a slingshot, repeatedly diving close to the sun to pick up more and more speed. It didn't achieve this through pure propulsion power. It borrowed energy from the orbital mechanics of the solar system itself. Before Parker, the record was held by Helios 2, a German-American probe launched in 1976, which reached 70 kilometers per second. The Voyager 1 spacecraft, which left our solar system and is now in interstellar space, is traveling at about 17 kilometers per second relative to the Sun. The space shuttle, when it was operational, traveled at about 7.8 kilometers per second in low Earth orbit. The Apollo missions that took humans to the Moon reached speeds of about 11 kilometers per second relative to Earth. Here's what's fascinating. These speeds represent roughly 0.05%, 0.023%, 0.006%, 0.003%, and 0.004% of the speed of light, respectively. We're talking about tiny fractions. Microscopic percentages, and the speed of light? That's 299,792 kilometers per second. It's the ultimate speed limit of the universe, at least as we currently understand physics. This brings us to the question that's probably foaming in your mind right now. Why can't we just build more powerful rockets? Why can't we just keep accelerating until we get to the speed of light? The answer is going to challenge everything you thought you knew about motion and energy. It's called the rocket equation, and it's the first major barrier standing between us and fast interstellar travel. Konstantin Tsiolkovsky, a Russian scientist, first formulated it in 1897, and it still governs every rocket we launch today. The rocket equation tells us that the amount of fuel you need doesn't increase linearly with the speed you want to achieve. It increases exponentially. Here's what that means in practical terms. If you want to go twice as fast, you don't need twice as much fuel. You need exponentially more fuel. And that fuel has mass, which means you need even more fuel to lift the fuel you're carrying. Think of it like this. Imagine you're trying to push a shopping cart. Easy enough. Now imagine the shopping cart is filled with other shopping carts, and those shopping carts are filled with other shopping carts, and so on. That's essentially what rocket propulsion becomes at higher speeds. The mass problem compounds on itself. But here's where things get really interesting, and I promise this will blow your mind. Even if we somehow solved the fuel problem, even if we had unlimited energy, we still couldn't reach the speed of light. And the reason why reveals something profound about the nature of reality itself. We're about to enter territory that will make you question everything you thought you knew about how the universe works. Stay with me. What if I told you that the speed of light isn't just a speed limit, but a fundamental property woven into the fabric of space-time itself? That it's less like a speed limit on a highway and more like the edge of reality? This is where Albert Einstein enters our story. In 1905, Einstein published his special theory of relativity, and it fundamentally changed how we understand motion, time, and space. He revealed something shocking. As objects with mass approach the speed of light, three bizarre things happen. First, time slows down for the moving object relative to stationary observers. This isn't science fiction. This is measured, verified reality. We've tested this with atomic clocks on airplanes, with particle accelerators, with GPS satellites. Time literally runs at different rates depending on how fast you're moving. Second, the object gets shorter in the direction of motion. This is called length contraction. At everyday speeds, this effect is negligible. But as you approach the speed of light, it becomes dramatic. If you could watch a spacecraft accelerating to 99% of the speed of light, you'd see it getting flatter and flatter, like it was being compressed. Third, and this is the killer, the object's mass increases. Not its physical size, but its relativistic mass, its resistance to further acceleration. As you approach the speed of light, your mass approaches infinity, and accelerating infinite mass requires infinite energy. This is why nothing with mass can reach the speed of light. It's not an engineering problem. It's a fundamental law of physics. Let me make this concrete with a thought experiment. Imagine you're in a spacecraft capable of constant acceleration at 1 gram, the same acceleration you feel from Earth's gravity. That's comfortable for human passengers. Starting from rest, here's how long it would take you to reach certain fractions of light speed. To reach 10% of light speed, about 35 days of constant acceleration. To reach 50% of light speed, about 6 months. To reach 90% of light speed, about 2.5 years. To reach 99% of light speed, about 6 years. To reach 99.9% of light speed, about 9.5 years. But here's the twist. These are the time frames as experienced by you on the spacecraft. For people back on Earth, due to time dilation, much more time would pass. And the energy required? It increases exponentially. To accelerate a single kilogram of matter to 99% of light speed requires about 2 trillion joules of energy. That's roughly the amount of energy in 50 tons of TNT for every kilogram. A typical spacecraft masses thousands of kilograms. You can see the problem. But wait, before you give up hope on fast space travel, let me tell you about the people who refuse to accept these limitations. Scientists and engineers who looked at the laws of physics and asked, how can we work within these laws to achieve something extraordinary? This is where propulsion technology gets really interesting. Because while we can't violate physics, we can get creative with how we use it. The fastest current propulsion method we have is chemical rockets. They work by burning fuel and expelling hot gas out the back. Newton's third law. Every action has an equal and opposite reaction. The problem? Chemical rockets are inefficient. The exhaust velocity, the speed at which the gases exit the rocket, is limited by chemistry. For the best chemical rockets, exhaust velocity tops out around 4.5 kilometers per second. Remember the rocket equation? The final velocity of your spacecraft is limited by your exhaust velocity. To go significantly faster than your exhaust velocity, you need exponentially more fuel. So engineers started thinking, what if we could increase the exhaust velocity? Enter ion drives. Instead of burning chemical fuel, ion drives use electricity to accelerate ions, charged particles, to very high speeds and shoot them out the back. The exhaust velocity of ion drives can reach 30 to 90 kilometers per second, up to 20 times faster than chemical rockets. NASA's Dawn spacecraft, which operated from 2007 to 2018, used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres. Over its lifetime, its ion drive changed the spacecraft's velocity by 11.5 kilometers per second. To achieve the same change with chemical rockets would have required carrying vastly more fuel, so much that the mission would have been impossible. But ion drives have a downside. They produce very low thrust. The Dawn spacecraft's ion drive produced about 90 millitons of thrust. That's about the weight of a single sheet of paper pressing down on your hand. It takes a long time to accelerate with such low thrust, though over months and years, you can build up significant speed. Then there's nuclear propulsion. This is where things get really interesting and controversial. The idea is simple. Nuclear reactions release far more energy than chemical reactions. If we could harness that energy for propulsion, we could achieve much higher speeds. One concept is nuclear thermal propulsion, where a nuclear reactor heats a propellant, like hydrogen, to extremely high temperatures, then expels it to create thrust. The exhaust velocity could reach 9 kilometers per second, twice that of chemical rockets. NASA and other space agencies are actively developing nuclear thermal propulsion for future Mars missions. But there's an even more powerful concept, nuclear pulse propulsion. Here's something that will blow your mind. In the 1950s and 60s, the United States seriously designed a spacecraft that would work by detonating nuclear bombs behind it. This wasn't science fiction. This was a real engineering project called Project Orion, led by physicist Freeman Dyson and others. The concept was brilliant in its audacity. You drop a nuclear bomb out the back of your spacecraft. It explodes, and a massive shock plate absorbs the blast, pushing the spacecraft forward. Then you drop another bomb, and another. You're essentially riding a series of nuclear explosions across the solar system. The calculations showed this could work. A large Orion spacecraft could potentially reach 5% of the speed of light. That's 15,000 kilometers per second. With a spacecraft like that, you could reach the nearest star system, Alpha Centauri, in about 85 years. Still a lifetime, but within the realm of possibility. The project was canceled in 1963, partly because of the Partial Nuclear Test Ban Treaty, which prohibited nuclear explosions in space. But the concept proved something important. With bold enough thinking, we could achieve a significant fraction of light speed using technology we understood, even in the 1960s. Now, let me introduce you to the scientists pushing the boundaries even further. Because if there's one thing humans are good at, it's refusing to accept limitations. Dr. Philip Lubin, a professor at the University of California, Santa Barbara, has been working on a concept called photonic propulsion using lasers to push spacecraft. The idea is to build a massive laser array on Earth or in space and use it to push ultra-lightweight spacecraft equipped with reflective sails. Here's what makes this revolutionary. The spacecraft carries no fuel. All the energy comes from the laser. This bypasses the rocket equation entirely. And photons from the laser move at the speed of light, so the exhaust velocity is literally the maximum possible. Lubin's calculations suggest that with a powerful enough laser array and a light enough spacecraft, we could accelerate a probe to 20% of the speed of light. That's 60,000 kilometers per second. At that speed, you could reach Alpha Centauri in about 20 years. The Breakthrough Starshot Initiative, funded by billionaire Yuri Milner and supported by Stephen Hawking before his death, is working toward exactly this goal. Their plan is to launch swarms of tiny spacecraft, each no bigger than a postage stamp, equipped with light sails, and push them to 20% of light speed using ground-based lasers. But here's the question that should be forming in your mind. Even if we can reach 20% of light speed, what about going faster? What about getting to 50%, 75%, 99% of light speed? Because remember, at those speeds, relativistic effects kick in. Time dilation becomes significant. The journey to distant stars doesn't just get shorter in distance. It gets shorter in time for the travelers. What we're about to explore next is going to fundamentally change how you think about interstellar travel, because the limitations aren't what you think they are. The real barriers are stranger, more fascinating, and in some ways, more surmountable than you ever imagined. Let me tell you something that sounds like science fiction, but is actually established physics. If you could travel at 99.9% of the speed of light, you could travel to the center of our galaxy, 26,000 light years away, in what would feel like just 35 years to you. Not 26,000 years, 35 years. This is time dilation in action, and it's one of the most counterintuitive consequences of special relativity. Time doesn't just slow down a little bit at high speeds. It slows down dramatically. At 99.9% of light speed, time moves 22 times slower for you than for people at rest. At 99.99% of light speed, it's 70 times slower. At 99.999% of light speed, it's 707 times slower. Think about what this means. A journey that would take millions of years for Earth-bound observers could take mere decades for the travelers. You could, in principle, visit distant galaxies within a human lifetime, your lifetime, even though eons would pass on. Earth. This was first clearly articulated by Einstein, but the implications for space travel were explored in detail by physicists like George Gamow in the 1940s, and later by Carl Sagan. It means that the universe is, in a strange sense, smaller for fast travelers than for stationary observers. But there's a cruel twist. While time dilation makes the journey shorter for you, everyone you left behind on Earth is aging normally. If you traveled to a star 100 light years away at 99% of light speed, the journey might feel like 14 years to you. But when you return, 200 years will have passed on Earth. Everyone you knew is dead. The world has changed beyond recognition. This is called the twin paradox, first described by Einstein in 1911. If one twin travels at relativistic speeds while the other stays on Earth, the traveling twin will age more slowly. When they reunite, the traveling twin is younger. This isn't a thought experiment anymore. We verified it with atomic clocks on spacecraft and even on commercial airplanes. It means that true interstellar travel, the kind that involves returning home, is fundamentally a one-way journey through time. You can visit the stars, but you can never truly come home. The home you left will be gone. This is the emotional weight that relativistic space travel carries. It's not just a technical challenge. It's a philosophical and psychological one. So how close to light speed can we realistically hope to travel? Let's look at the most ambitious propulsion concepts that are theoretically possible with known physics. The most powerful concept is antimatter propulsion. When matter and antimatter meet, they annihilate each other completely, converting all their mass into pure energy according to Einstein's famous equation E equals mc. No other reaction is more efficient. It's 100% conversion of mass to energy, compared to about 0.7% for nuclear fusion, and a tiny fraction of a percent for chemical reactions. Dr. Robert Forward, a physicist and aerospace engineer who worked on this concept in the 1980s, calculated that an antimatter rocket could theoretically reach 50% of light speed or higher. The exhaust velocity would be close to light speed itself. The problem? Producing and storing antimatter. Currently, we can only create tiny amounts of antimatter in particle accelerators at a cost of roughly $100 billion per gram. And storing antimatter is incredibly difficult because it annihilates on contact with any normal matter. You need magnetic bottles or other exotic storage methods. Still, for a sufficiently advanced civilization, antimatter propulsion might be feasible, and 50% of light speed would make the nearest stars reachable within a decade or two of travel time. Then there's the Bussard ramjet, a concept proposed by physicist Robert Bussard in 1960. The idea is audacious. Instead of carrying fuel, scoop it up as you go. Space isn't truly empty. There are, on average, about 1 hydrogen atom per cubic centimeter in interstellar space. A ramjet would use a huge magnetic field kilometers wide to scoop up these hydrogen atoms, compress them, fuse them in a nuclear reactor, and use the energy for propulsion. If it worked, a ramjet could accelerate continuously as long as it's moving through interstellar hydrogen. Theoretically, you could approach very close to light speed, perhaps 90% or higher. The catch? The magnetic scoop would need to be enormous. And at high speeds, the hydrogen atoms you're scooping up would actually start acting like a radiation hazard, slowing you down. Some physicists, like Dr. Daniel Whitmire, who analyzed this in 1975, have argued that ramjets might be self-limiting. They'd reach a maximum speed and couldn't go faster. But for a civilization willing to build megastructures, it's not out of the question. Here's what's really going to mess with your head. All of these propulsion methods, all of them, are working within the speed of light limit. We're trying to go fast, but we're still stuck below that ultimate barrier. But what if I told you there might be ways to cheat? Not by going faster than light, but by changing the structure of space itself. This is where we enter the realm of exotic physics. And it's going to sound like fantasy, but it's based on real mathematics derived from Einstein's general theory of relativity. In 1994, a physicist named Miguel Alcubierre published a paper that changed how scientists think about faster-than-light travel. He proposed something called the Alcubierre drive, or warp drive. The concept: instead of moving through space at faster than light, you compress the space in front of your spacecraft and expand the space behind it. You create a warp bubble where space itself is moving, carrying the spacecraft along with it. Inside the bubble, you're not moving at all relative to the local space. so you never violate special relativity. But relative to the universe outside the bubble, you can be moving faster than light. The mathematics work. General relativity allows for this kind of space deformation. In principle, there's no speed limit. You could traverse the entire galaxy in days or hours. And this is a massive, but the Alcubierre drive requires something called exotic matter or negative energy. This is matter or energy with negative mass or negative energy density, and we don't know if it exists. Some quantum field theory suggests negative energy might be possible in certain situations, but producing it in the quantities needed for a warp drive? That's purely speculative. Dr. Harold White, a physicist at NASA's Johnson Space Center, has worked on variations of the Alcubierre drive that might require less exotic matter. In 2021, Dr. Eric Lentz proposed a different warp drive concept using positive energy densities. These are all highly theoretical, but they represent serious scientific inquiry. The point is this: faster than light travel isn't ruled out by physics. It's just that every method we can think of requires technology or materials we don't have and might not be possible. But here's what keeps physicists up at night. The universe is 13.8 billion years old. If faster than light travel is possible, why haven't we seen evidence of it? Where are all the alien civilizations zipping around at warp speed? This is part of the Fermi paradox, named after physicist Enrico Fermi. And the answer might be that faster than light travel simply isn't possible, no matter how advanced you are. The speed of light might be a true, inviolable limit for all civilizations everywhere. So let me ask you a question. Given these limitations, given that we might never travel faster than light, given that even getting to a significant fraction of light speed requires technologies we don't have, should we give up on interstellar travel? The answer is going to surprise you, because what we're going to explore next is how human ingenuity has found ways to make interstellar travel feasible even within our limitations. The solutions are creative, bizarre, and absolutely fascinating. And they reveal something profound about what it means to be human in a vast, seemingly unreachable universe. What if I told you that the key to reaching the stars isn't going faster, but thinking longer? That we don't need to compress the journey time, we need to expand our concept of what a journey means? This is where we enter the world of generation ships, and it completely reframes the question of space travel. A generation ship is exactly what it sounds like. A spacecraft so large that it becomes a self-sustaining habitat, and so slow that multiple generations of people will live and die aboard it before reaching the destination. You don't send astronauts. You send the civilization. The concept was first seriously explored by physicist J.D. Burrell in 1929, and later refined by many others, including Dr. Gerard O'Neill in the 1970s with his famous O'Neill cylinder's massive rotating space habitats that could house thousands or millions of people. Here's the math. Even with relatively modest propulsion systems, we could build a generation ship that travels at 1% of light speed. That's 3,000 kilometers per second. Still much faster than anything we've built, but theoretically achievable with something like nuclear pulse propulsion or fusion drives. At that speed, reaching Alpha Centauri would take about 430 years. That's roughly 15 to 20 generations of humans. Think about what this means. People would be born on the ship, live their entire lives on the ship, and die on the ship, never seeing either Earth or the destination. The entire concept of home would be the ship itself. Children would grow up learning about Earth as a mythical place their ancestors came from, and learning about the destination world as a promised land they're traveling toward, but will never see. This raises profound psychological and sociological questions. Dr. Cameron Smith, an anthropologist at Portland State University, has studied the minimum viable population for a generation ship. His research suggests you'd need at least 14,000 to 44,000 people to maintain genetic diversity and avoid inbreeding over such long timescales. That's not a ship, that's a small city. You'd need to create an entirely self-sustaining ecosystem. Farms to grow food, systems to recycle air and water, manufacturing capabilities to maintain and repair the ship, education systems to preserve knowledge across generations, legal and social systems to govern the population, cultural traditions to maintain purpose and identity. And you'd need to prevent social collapse over centuries. What happens when a generation decides they don't want to continue the journey? What if there's a civil war on board? What if the destination turns out to be unsuitable and they can't turn back? But here's where it gets even stranger. Some scientists have proposed that instead of sending humans, we should send the means to create humans. This is called the embryo space colonization concept, proposed by researchers including Dr. John Moore. The idea: send frozen embryos along with artificial wombs and robotic caretakers. When the ship arrives at the destination, the robots raise the first generation of humans, who then build a civilization from scratch. This solves the generation ship problems. No need to sustain a population for centuries. No risk of social breakdown during transit. But it raises even deeper ethical questions. Is it moral to create humans who have no parents, no human caregivers, no cultural heritage, except what robots teach them? Or we could go even further. Send just DNA and the technology to reconstruct humans from that DNA. Or send detailed scans of human brains and bodies to be reconstructed using advanced 3D printing technology at the destination. You wouldn't be sending the original people, you'd be sending copies. Are those copies the same people? Do they have the same rights? The same identity? These aren't just engineering questions. They're philosophical ones about the nature of identity, consciousness, and what it means to be human. Here's something that will absolutely blow your mind. There are scientists who argue we shouldn't send biological humans at all. We should send artificial intelligence. Dr. Martin Rees, the Astronomer Royal of the United Kingdom, has suggested that by the time we're capable of interstellar travel, we might have developed AI that surpasses human intelligence. And AI doesn't need life support, doesn't need food or water, doesn't age, can be backed up, can potentially be transmitted as pure information and reconstructed at the destination. An AI probe could be small, light, and fast, much faster than any crewed spacecraft. It could explore, collect data, and beam information back to Earth at light speed. If the goal is to explore the universe and expand human knowledge, AI might be far more effective than sending biological humans. But then comes the question, if we send AI instead of humans, are we still exploring? Or have we created a successor species that explores in our place while we stay behind? Have we, in essence, made ourselves obsolete? This is the question that haunts every discussion of advanced space exploration. What is the goal? Is it to spread human biology, human consciousness, human values and knowledge? And do those things require actual humans, or can they be carried by other means? Let me bring this back down to Earth, literally, and connect it to your life right now. Because everything we've been talking about isn't just abstract science. It reveals something profound about human nature and how we think about our place in the universe. Right now, as you listen to this, you are on a spacecraft. It's called Earth, and it's traveling through space at hundreds of thousands of kilometers per hour. It's been traveling for 4.5 billion years. It's the most successful generation ship ever created, a self-sustaining habitat that has supported life for eons as it orbits the sun, which itself orbits the galaxy. You are already a space traveler. You always have been. But here's what the limitations we discussed reveal about us. We're a species that refuses to accept boundaries. When we learned we couldn't fly, we invented airplanes. When we learned space was inhospitable, we built spacesuits and space stations. When we learned the stars were impossibly far away, we started designing generation ships, laser sails, antimatter drives, and warp bubbles. The question of how fast we can travel in space isn't really about speed. It's about perseverance. It's about whether we're willing to commit to goals that extend beyond our lifetimes, beyond our children's lifetimes, beyond many generations. And here's what's remarkable. We've already proven we can do this. The cathedrals of medieval Europe took centuries to build. The people who laid the foundations knew they'd never see the completed building. They built anyway. The Great Wall of China took over 2,000 years to complete. The people who started it knew their descendants would continue the work. They started anyway. Interstellar travel is the ultimate cathedral. It's a project that requires us to think not just across our lifetime, but across the lifetime of our species. And that changes how you think about your own life. Because you're part of a long line of humans stretching back to our earliest ancestors and forward to descendants you'll never meet. Every choice you make, every contribution you make to human knowledge or human civilization is a stone laid in a cathedral you'll never see completed. The fact that we're even having this conversation, that we're seriously planning missions to other star systems, says something beautiful about humanity. We're a species that looks at the impossible and treats it as a challenge. We're a species that plants trees under whose shade we'll never sit. But let me ask you something that might make you uncomfortable. What if we're thinking about this all wrong? What if the question isn't how fast can we travel in space, but should we travel in space at all? Because everything we've discussed has enormous costs. And the choices we make about space exploration reveal our values and priorities as a species. What comes next is going to challenge your assumptions about why we explore, what we hope to find, and whether the universe wants us out there at all. And fair warning, some of these answers are darker than you might expect. Let me tell you about something called the relativistic kill vehicle, because this is where our quest for speed in space takes a dark turn. When you accelerate something to a significant fraction of light speed, it doesn't just become a fast object. It becomes a weapon of unimaginable power. The kinetic energy, the energy of motion, increases dramatically with speed. A 1 kilogram object traveling at 90% of light speed carries the kinetic energy equivalent of 10,000 megatons of TNT. That's about 200 times more powerful than the largest nuclear weapon ever detonated. This was calculated by physicists studying potential space warfare scenarios, including Dr. Robert Freitas, who wrote extensively about self-replicating spacecraft in the 1980s. A civilization that has mastered near-light speed travel has also mastered weapons that could sterilize planets from light years away. You don't need bombs or missiles. You just need to throw something fast enough. This is one solution to the Fermi paradox. Maybe advanced civilizations stay quiet and hidden because the universe is a dark forest, and any civilization that reveals itself becomes a target. Maybe the speed we seek isn't just for exploration, it's also for defense or offense. And there's another dark consideration. The faster we can travel, the more dangerous space becomes to us. At high relativistic speeds, even tiny particles become hazards. A grain of sand hitting your spacecraft at 90% of light speed would release as much energy as several kilograms of TNT. The interstellar medium, those sparse hydrogen atoms we talked about, becomes deadly radiation. Dr. William Edelstein, a physicist at Johns Hopkins University, calculated in 2012 that at just 50% of light speed, the radiation from interstellar hydrogen atoms would be fatal to human crew within minutes without massive shielding. And shielding adds mass, which makes acceleration harder, which brings us back to the rocket equation. The faster we want to go, the more dangerous the journey becomes. There's a cruel trade-off, speed versus safety. But here's the really uncomfortable question. Should we be trying to leave Earth at all? Every dollar, every joule of energy, every ounce of scientific genius we devote to space travel is a dollar, joule, and genius not devoted to solving problems here on Earth. Climate change, poverty, disease, inequality, These are urgent, immediate problems. Is it moral to spend resources on reaching Alpha Centauri when we haven't solved hunger on our own planet? This is the debate that has raged since the beginning of the space age. Carl Sagan, who passionately advocated for space exploration, also argued in his 1994 book Pale Blue Dot that we need to solve our problems at home. But he also said that space exploration represents the best aspects of humanity: our curiosity, our drive to explore, our refusal to accept limits. He argued that the technological developments from space programs benefit life on Earth. Others, like critics such as economist Amitai Etzioni, have argued that space exploration is a luxury for the wealthy, while billions suffer. And money spent on a single space mission could fund schools, hospitals, clean water systems. There's no easy answer. But here's what's fascinating. The question itself reveals something about us. We're a species capable of caring about both the immediate and the infinite. We can worry about our next meal and also wonder what's beyond the stars. That duality, practicality, and dreaminess is uniquely human. And historically, the societies that stopped exploring, stopped asking questions, stopped pushing boundaries, those societies stagnated and declined. Not because exploration is inherently good, but because the mindset that drives exploration, curiosity, innovation, problem solving is the same mindset that drives progress in every field. The Apollo program, which put humans on the moon, led to developments in computing, materials science, telecommunications, and medicine that revolutionized life on Earth. The drive to solve the problems of space travel forces us to become better at solving problems in general. But let's dig deeper into the actual barriers we face right now. Because beyond the physics, beyond the engineering, there are practical limitations that are stopping us from traveling fast in space today. Money is the first barrier. The Parker Solar Probe, our fastest spacecraft, cost about $1.5 billion. The Apollo program cost roughly $280 billion in today's dollars. The International Space Station has cost over $150 billion. These are enormous sums, but they're nothing compared to what an interstellar mission would require. Dr. Andreas Eng, who has studied the economics of interstellar travel extensively, estimates that a crewed mission to Alpha Centauri, using current or near-term technology, would cost somewhere between 0.5% and 5% of world GDP sustained over decades. That's hundreds of trillions of dollars. It would require international cooperation on a scale humanity has never achieved. For comparison, the entire Apollo program at its peak consumed about 4% of the US federal budget. An interstellar mission would require that level of commitment, but sustained not for a decade, but for a century or more. It would require political will that transcends national boundaries, election cycles, and human lifespans. Here's what will blow your mind. Despite all these barriers, we could technically launch an interstellar probe right now. Not a fast one, not a sophisticated one, but we could do it. The Voyager 1 spacecraft, launched in 1977, has left the solar system and is now in interstellar space. It's traveling at 17 kilometers per second. At that speed, it would reach Alpha Centauri in about 75,000 years if it were headed in that direction, which it's not. But the point is, we've already proved we can build something that escapes the sun's gravity and enters interstellar space. If we launched a similar probe tomorrow, using slightly better technology ion drives, gravity assists from Jupiter, we could maybe cut that time to 50,000 years. Still unimaginably long, but technically feasible. The question isn't, can we do it? The question is, why would we? A mission that takes 50,000 years is useless for gathering data we'd ever receive. But here's the thing. 50,000 years ago, humans were still living in small tribes, just beginning to develop complex language. Who knows what humanity will be like 50,000 years from now? Maybe launching these incredibly slow probes is planting seeds for a future civilization to harvest. Or maybe And this is the darker possibility. We won't be around in 50,000 years. Maybe the window for interstellar travel is narrow, and we're in it right now. This brings us to one of the most unsettling ideas in astrobiology, proposed by economist Robin Hanson in 1996, the Great Filter. The concept is this: somewhere between the emergence of life and becoming an advanced spacefaring civilization, there's a barrier, a filter that's extremely difficult to pass through. We don't see any evidence of advanced alien civilizations in our galaxy. No radio signals, no megastructures, no signs of interstellar travel, despite billions of years for such civilizations to arise and spread. This is the Fermi paradox again. The Great Filter is the explanation. Something prevents most or all civilizations from reaching the stars. The terrifying question is the filter behind us or ahead of us? If it's behind us, if the difficult step was the emergence of life, or the evolution of intelligence, or the development of technology, then we're incredibly rare, but our future is bright. We've passed the test. But if the filter is ahead of us, that means something destroys or prevents civilizations from spreading to the stars. Nuclear war, climate catastrophe, artificial intelligence gone wrong, a physics limitation we haven't discovered yet. Something stops every civilization before they can achieve fast interstellar travel. And here's why this connects to our question about speed. The faster we can travel, the better our chances of surviving the Great Filter. If we can spread to multiple star systems, humanity becomes much harder to extinguish. A catastrophe on Earth wouldn't mean extinction. We'd have backups. Speed in space isn't just about exploration. It's about survival. It's about insurance against existential risk. Dr. Nick Bostrom, a philosopher at Oxford University, has written extensively about existential risks, threats that could end human civilization or cause human extinction. He argues that becoming a spacefaring species, spreading across multiple worlds and star systems, dramatically reduces our existential risk. We become antifragile. We get stronger from shocks rather than weaker. But to do that, we need to travel fast enough that the journeys are feasible within human timescales. Generation ships taking thousands of years are vulnerable. A disaster could destroy them in transit. Fast ships traveling at 10%, 20%, 50% of light speed can make the journey quickly enough to reduce that vulnerability. So the quest for speed in space isn't just about curiosity or adventure. It might be about the survival of our species. Now let me tell you about something that's happening right now that gives me hope. Because while we've spent a lot of time talking about the limitations and barriers, there are real, concrete projects underway that are pushing the boundaries. Breakthrough Starshot, which I mentioned earlier, is planning to launch its first test missions in the coming decades. The concept is to send thousands of tiny spacecraft, each called a Starship equipped with light sails, and accelerate them using ground-based lasers to 20% of light speed. At that velocity, they could reach Alpha Centauri in about 20 years and send back data using tiny onboard lasers to beam information to Earth. The project is led by Dr. Pete Worden, former director of NASA's Ames Research Center, with backing from Yuri Milner and initial endorsement from Stephen Hawking. They're not just dreaming, they're engineering. They're running tests on laser arrays, developing the ultra-lightweight sails, miniaturizing electronics. This is happening. If successful, your lifetime could see the first human-made object arriving at another star system. Think about that. You could live to see images beamed back from Alpha Centauri, worlds 4.37 light-years away, captured by cameras we launched from Earth. NASA is also developing nuclear thermal propulsion for Mars missions, with plans to test the technology in the 2020s and 2030s. This isn't for interstellar travel, but it's a stepping stone. Each advancement in propulsion technology brings us closer to the speeds we need for the stars. Private companies are getting involved too. Companies like SpaceX are driving down the cost of getting to orbit, which is the first step of any journey into deep space. When Elon Musk talks about making humanity a multi-planetary species, he's talking about the first step toward becoming an interstellar species. And fusion energy research is advancing. If we can achieve practical fusion power, and several projects including ITER in France, and private ventures like Commonwealth Fusion Systems are getting closer, we unlock new possibilities for propulsion. Fusion drives could potentially reach several percent of light speed, making the outer solar system, and even nearby stars, reachable within human lifetimes. Here's something that will mess with your head. There are scientists who believe we might already be traveling as fast as we can, and we don't even realize it. This is based on something called the anthropic principle and the simulation hypothesis. The idea goes like this. If we're living in a simulation, a computer-generated reality, then the physics we observe, including the speed of light limit, might not be fundamental properties of reality. They might be computational constraints. The speed of light might be like the frame rate of a video game. Go faster than the engine can handle, and things start glitching. The reason we can't exceed light speed isn't because of some deep physical law, but because the simulation can't process information faster than that. Now, I'm not saying I believe this, but it's a legitimate hypothesis discussed by philosophers like Nick Bostrom and physicists like James Gates Jr., who found error-correcting code in equations describing fundamental particles, the same kind of code used in web browsers. If we're in a simulation, then traveling fast in space might mean something completely different than we think. It might mean hacking the code rather than building faster rockets. Stay with me, because we're approaching the end of this journey, and I want to bring everything together in a way that will completely reframe how you think about speed, space, and your place in all of this. What I'm about to share with you in these final sections is going to tie together everything we've discussed and show you why this question matters to you personally, right now, today. Let me tell you what I think is the real limit on how fast we can travel in space, and it's not what you expect. It's not physics. It's not engineering. It's not even money. It's imagination. Every major breakthrough in space travel has come from someone who refused to accept the prevailing assumptions. Konstantin Tsiolkovsky, who derived the rocket equation, was a Russian schoolteacher who imagined space elevators and rotating habitats in the 1890s, when most people thought spaceflight was fantasy. Robert Goddard, who built the first liquid-fueled rocket in 1926, was mocked by the New York Times for suggesting rockets could work in the vacuum of space. The Times published a correction in 1969, the day after Apollo 11 launched, admitting they were wrong. Wernher von Braun imagined missions to Mars in the 1950s, when we hadn't even reached orbit yet. His visions inspired generations of engineers who made spaceflight real. The scientists working on warp drives, laser sails, antimatter propulsion, they're not working on these things because they know they'll work. They're working on them because they refuse to accept that we're stuck at 0.05% of light speed forever. And here's what history teaches us. The things that seem impossible today become routine tomorrow. In 1900, the idea of flying was ridiculous. In 1903, the Wright brothers flew. By 1969, we were landing on the moon. That's 66 years from first flight to moon landing. In 1945, computers were room-sized machines that could barely do basic arithmetic. Today, you're probably listening to this on a device millions of times more powerful than those early computers. A device you carry in your pocket. The rate of technological progress is accelerating. Things that once took centuries now take decades. Things that took decades now take years. So when someone asks me, how fast can we travel in space right now? I answer with another question. How fast will we be traveling in 50 years? In 100 years? Because the answer changes. The answer is always changing. And the direction it changes depends on whether we give up or keep pushing. Let me make this personal. You listening to this right now are part of this story. Every time you share curiosity about space, every time you support science education, every time you vote for leaders who fund research, every time you choose a career in STEM fields or encourage a child to look up at the stars, you're contributing to humanity's journey to the stars. The spacecraft that will one day travel to Alpha Centauri at 20% of light speed, or 50%, or whatever speed we eventually achieve, that spacecraft is being built right now, not with metal and fuel, but with ideas and inspiration and education and persistence. You're part of the project. You always have been. Here's the final thing that will blow your mind, and it's going to bring everything full circle. Remember how I said at 99.9% of light speed, you could travel to the center of the galaxy in 35 years of your time due to time dilation? Well, at 99.99999% of light speed adding more 9 south, you could travel to the edge of the observable universe, 46 billion light years away, in less than a human lifetime as experienced by you. The entire observable universe becomes accessible within a single human lifespan. The barrier isn't really space or time. The barrier is energy. If we could somehow accelerate something to that speed, and that's an enormously big if the universe becomes small. This means something profound. The universe isn't too big for us. We're not trapped on this pale blue dot by distance or time. We're only limited by how clever we can be with energy and propulsion. The universe is waiting. It's patient. And it's not impossible to reach, just very, very hard. So let me answer the question I started with. How fast can we travel in space right now? The literal answer, 163 kilometers per second, 0.054% of light speed, achieved by the Parker Solar Probe using gravity assists. The practical answer for human spaceflight, about 11 kilometers per second, or 0.004% of light speed, achieved by the Apollo missions. The realistic answer for what we could achieve with focused effort and current technology, probably 5 to 10% of light speed, using laser sails or advanced nuclear propulsion, making nearby stars reachable within decades or a century. The theoretical answer, based on known physics, up to about 99.9999% of light speed, making the entire observable universe accessible if we can solve the energy and engineering challenges. The philosophical answer, we can travel as fast as we're willing to imagine, as fast as we're willing to work for, as fast as we refuse to give up on. But here's what I want you to take away from these 3 hours we've spent together. The question of how fast we can travel in space is really a question about who we are as a species. Are we the kind of species that looks at impossible challenges and says not yet instead of never? Are we the kind that plants trees for our descendants? Are we the kind that reaches for the stars even when the stars are impossibly far away? History suggests we are. Every generation faces challenges that seem insurmountable, and every generation finds a way forward, not always quickly, not always successfully, but forward. You are living at a unique moment in human history. You're alive at the very beginning of humanity's expansion beyond Earth. The first permanent human presence in space, the International Space Station, is just over 2 decades old. The first commercial space flights are just happening now. The first missions to establish permanent bases on the Moon and Mars are being planned for your lifetime. And yes, the first interstellar probes, the first human-made objects that will travel to other star systems with the intention of sending back. Data those are being designed and tested right now. You're not watching history. You're living it. You're part of it. So here's my final question for you. Knowing what you now know about the challenges and possibilities of traveling fast in space, knowing that it might take centuries or millennia to reach the stars, knowing that it will require sacrifice and dedication and resources and imagination, do you think we should try? Drop your answer in the comments. Tell me whether you think humanity should invest in reaching the stars, or whether we should focus on Earth. Tell me whether you think we'll ever break the light speed barrier, or whether we're stuck with slow, patient generation ship journeys. Tell me what you think the great filter is, and whether we've passed it or it's still ahead of us. And if this video changed how you think about space, about speed, about humanity's future, about your place in the cosmic story, hit that like button and share this with someone who needs to have their mind expanded. Subscribe to this channel because we're going to keep exploring the biggest questions humanity faces, the questions that challenge our assumptions and force us to think bigger. The stars are far away, but they're not unreachable. Not if we refuse to give up, not if we keep pushing, not if each generation does its part to move us forward. Thank you for spending these 3 hours with me on this journey through space, time, physics, and human ambition. Now go look up at the night sky. Those stars are waiting, and we're coming. Maybe not today, maybe not in your lifetime, but we're coming. Because that's what humans do. We explore, we wonder, we reach, we refuse to be contained. And one day, in a future you've helped build, someone will look back at this moment, this era when we were still crawling at 0.05% of light speed, and they'll smile at how primitive we were. And then they'll engage their warp drive, or their antimatter engine, or their technology we can't even imagine yet, and they'll travel to the stars in days or hours or minutes. And it will be because people like you refuse to give up on the dream. Safe travels wherever you're going. And remember, you're already moving at hundreds of thousands of kilometers per hour. You're already a space traveler. You always have been. Before you click away, let me leave you with one more thought that's been haunting me throughout this entire conversation. Something that ties together everything we've discussed in a way that might fundamentally alter how you see yourself and your purpose. We've talked about speeds, about physics, about propulsion systems and generation ships. We've talked about the barriers, both physical and imaginative, that stand between us and the stars. But there's one aspect of this question we haven't fully explored, and it's perhaps the most important one. What if the real speed limit isn't about how fast our spacecraft can move, but about how fast our thinking can evolve? Consider this. Every major advancement in space travel has required us to fundamentally reimagine what's possible. The Wright brothers didn't just build a better horse-drawn carriage. They invented a completely new category of transportation. The Apollo engineers didn't just make bigger rockets. They created an entirely new approach to systems engineering, inventing technologies and techniques that didn't exist. Right now, we're thinking about traveling to the stars using variations of technologies we already understand. Rockets, nuclear, power, lasers, even antimatter and warp drives are extensions of physics we've already discovered. But what if the breakthrough that enables true fast interstellar travel is something we haven't even conceived of yet? Something that requires a complete paradigm shift in how we understand reality? Think about it this way. If you transported someone from the year 1000 CE to today and tried to explain how the internet works, how information travels instantaneously around the world, how you can see and talk to someone on the opposite side of the planet in real time, they wouldn't just be confused. They'd lack the entire conceptual framework to even understand the explanation. The ideas of electricity, electromagnetic waves, computers, satellites, none of these would make sense because they don't have the prerequisite knowledge. We might be in the same position right now regarding fast interstellar travel. We might be medieval peasants trying to imagine the internet. The real solution might require understanding aspects of physics we haven't discovered yet, manipulating dimensions we don't know exist, or harnessing energies we can't yet detect. And here's what makes this simultaneously exciting and terrifying. We can't know what we don't know. We can't imagine the unimaginable. The breakthrough that enables us to travel to distant galaxies within a human lifetime might come from a direction we're not even looking. Maybe it's in quantum mechanics, something about quantum entanglement, or the way particles can be in multiple states simultaneously. Maybe it's in our understanding of consciousness itself. Some physicists, like Dr. Roger Penrose, have proposed connections between quantum mechanics and consciousness. What if consciousness is somehow fundamental to the universe, and understanding that connection gives us access to new ways of manipulating space and time? Or maybe, and this is truly mind-bending, the answer lies not in going faster, but in redefining what travel means. What if you don't need to physically move from point A to point B? What if you could somehow transfer your consciousness, your information, your essential pattern across vast distances? You wouldn't be traveling through space. You'd be transmitting yourself as data and reconstructing on the other end. This isn't as far-fetched as it sounds. Your consciousness, your thoughts, your memories, they're all patterns of information encoded in the neural connections of your brain. If we could map those patterns completely and transmit them at the speed of light, you could arrive at Alpha Centauri in just 4.37 years. No spacecraft needed. No fuel, no propulsion. Of course, this raises that philosophical question again. Is the reconstructed you still you? If we copy your pattern and rebuild it somewhere else, is that continuation or death and replacement? These aren't just thought experiments. If this becomes a real technology, these questions become matters of life, death, and identity that society will have to grapple with. But here's what I really want you to understand. The fact that we're even having these conversations, the fact that we're seriously discussing antimatter drives and warp bubbles and consciousness transfer, this is unprecedented in human history. For 99.9% of human existence, the stars were unreachable, incomprehensible divine lights. Now we're engineering missions to reach them. The speed of our technological progress is itself a kind of velocity, not through space, but through the landscape of possibilities. And that velocity is accelerating. The time between impossible and routine is compressing. This means that the answer to how fast can we travel in space is quite literally changing as you listen to these words. Somewhere right now, a researcher might be making a discovery that will double or triple the speeds we can achieve, or discovering a fundamental principle that renders our current approaches obsolete. You want to know what truly keeps me up at night? It's not whether we'll reach the stars. I'm confident we will eventually, assuming we survive as a species. What keeps me up is wondering whether we'll be fast enough. Because the universe is not static, it's expanding. And due to dark energy, that expansion is accelerating. Distant galaxies are moving away from us faster and faster. There will come a time billions of years from now, but still when distant galaxies accelerate beyond the point where we could ever reach them, even traveling at light speed, the observable universe is shrinking in terms of what's accessible. Every moment we wait, the universe becomes a little more unreachable. This creates a cosmic urgency. The window for exploring the universe isn't infinite. It's vast, yes, billions of years. But it's closing. The faster we can travel, the more of the universe we can reach before it accelerates beyond our grasp. The speed of our spacecraft is racing against the speed of cosmic expansion. And that, more than anything, is why this question matters. How fast can we travel in space right now? Not fast enough. Not yet, but we're working on it. And every day, every year, every generation, we get a little bit faster. We push a little bit further. We refuse to accept that the universe's grandest wonders will forever remain beyond our reach. So when you look up at the stars tonight, and I really hope you do, remember this. Those points of light represent places we can go. Not easily, not quickly, maybe not in your lifetime, but eventually, because we're humans, and humans don't stay put. We never have. We walked out of Africa and spread across Earth. We crossed oceans in wooden boats, not knowing what was on the other side. We climbed mountains because they were there. We went to the moon because it seemed impossible. And we'll go to the stars, at whatever speed we can manage, building on the work of everyone who came before us. creating possibilities for everyone who comes after. You're part of that chain. Your curiosity matters. Your support for science and exploration matters. Your refusal to accept limitations matters. The stars are waiting, and so is the future. Let's go meet them.